everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 18th lecture. In this lecture, we will be continuing with formal verification. In the earlier lectures, we had seen that two formal verification techniques that made the formal verification tools scalable for VLSI applications where Boolean function representations using binary decision diagrams and Boolean satisfiability solvers which were quite efficient. So, in the last lecture we had looked into the BDD representation, and in this lecture we will be looking at Boolean satisfiability problem solvers or tools that solve the Boolean satisfiability problem, or they are also known as SAT solvers. Now, let us first understand what is the satisfiability problem. Suppose we are given a function f is equal to y is equal to f x1, x2, x3 to xn, where x1, x2, x3 to xn these are Boolean variables, and we are asked the question that can y be evaluated to 1 by any assignment of the variables x1, x2, x3, xn, right. So, all these variables can take only binary values, meaning zeros or and 1. Can we find a combination of values for these x1, x2, xn such that the y can be evaluated to 1? If it is, if yes, then f is said to be a satisfiable instance or SAT instance. And if we are not able to find, or it does not exist, if there is there does not exist any assignment of these Boolean variables such that y can become 1, then we say that y is an unsatisfiable instance or unsat instance. Now, let us take an example and understand it. Suppose we are given a function y f is equal to f x1, x2, x3 is equal to x1, x2 plus x1, x3 x plus x2 dash x3. Now, is it a SAT instance? We can easily see that if there are three terms, right, these three product terms. Now, if any of these product terms are made 1, then f can become 1, right. So, there can be many possible cases. For example, if we take x1 is equal to 1 and x2 is equal to 1, this product term will be 1 and y f will be 1, right. So, the function f can be evaluated to 1 by many assignments. For example, x1 is equal to 0, x2 is equal to 0 and x3 is equal to 1, right. If we take this assignment, then this term, the last term will become 1, right, and therefore, f will become 1, right. Similarly, there are other assignments. Even if there was one assignment, we would have said that f is satisfiable, meaning that, so since there are in this case there are 4 such assignments for which the value of f comes out to be 1, we say that this is a SAT instance. Now, even if there was existed only one assignment, any assignment such that f was 1, we would have said that the f is a satisfiable instance. Now, suppose let us take another function g x1, x2, x3 is x1 plus x2 into x1 plus x1 bar plus x2 bar and x1 bar x2 into x1 plus x3 and ANDed with x1 plus x3 bar. Now, is it a SAT instance? Now, to verify it, we can simply draw a truth table. For example, we can say that x1, x2, x3. Now, there are 3 variables and therefore, there are 2 to the power 3 or 8 combinations. For example, x1 can take 0, x2 0 and x3 0 or x1 0, x2 0 and 1 and so these are four possible cases. Similarly, there will be 4 other cases in which we will have 1, 1, 1, 1 here, and the x2, x3 will take 0, 0, 0, 1, 1, 0 and 1, 1, right. So, these are the 8 possible cases. Now, for each of them we can say what will be the value of g. For example, if we take x1, x2, x3 is equal to 0, what will happen? Now, if any of this term becomes 0, then g will be 0, right. Now, in this case x1 plus x2 becomes takes a value 0. So, this one will be of course 0, right, and in here also x1 plus x2 is 0. So, this one will also be 0, and we can say that these two will always be 0. Similarly, if x1 dash plus x2 dash this becomes 0, right, then also this function will become 0, right. For example, if we take this where x1 is equal to 1 and x2 is equal to 1, this one will become 0 and this one will also become 0, right. Similarly, we can evaluate for all the cases, and it turns out that if we do it for all the cases, we will say get that all the for all cases the value of g will be 0, right. Now, if that happens for a function, then we say that it is an unsat function. So, in this case we can g cannot be evaluated to 1 for any combination of values of x1, x2, x3, and therefore, it is an example of an unsat instance. So, this is the basic problem of satisfiability. So, given a function, whether we can evaluate it to 1 or not. If we yes, then we can say that this function is sat, otherwise it is unsat, right. Now, what are inputs to a SAT solver? So, SAT solvers typically takes input in terms of conjunctive normal form or CNF representation. So, this is a special type of representation of a Boolean function. What it is, we just see. Now, what is CNF? CNF is AND of clauses, AND of clauses. And what is a clause? Clauses are all or of literals, or of literals. So, a function represented in CNF is AND of various clauses, and clauses are basically, so AND of clauses, 1 clause, 2 clause, 3 clause and so on, and these are ANDed together, and each clause is are OR of literals, meaning that we have plus, plus and we will have literals here, right, and so on. So, and what are literals? We have seen earlier that literals are variable or its complement. So, let us see an example of a function represented in CNF. So, this is a function which is represented in CNF. So, we have variables in this as x1, x2, x3, and what are the literals? Literals are x1, x2, x1 bar or x1 dash and x3 dash, right. These are the literals that appear in this Boolean function. And what are the clauses? This is one clause, this is another clause, and this is third clause. So, there are 3 clauses in this case. Why? These are clauses are OR of literals. So, these are all OR of literals, right. And we have finally taken the AND of, so dot is implicit, right. So, we have ANDed with, so all these clauses are ANDed together and we got a function f in a CNF representation. Now, why to use a CNF in SAT solver? Why do we use a special representation of a Boolean function for a SAT solver? Because it reduces to 0 if any of the clause is 0. Now, in this, if we represent a Boolean function as in CNF, if any of these clauses takes a value 0, then the whole function takes a value 0, right. And therefore, what it means that to make a function satisfiable, all its clauses must be made 1, all of them have to be made 1, then only the function is satisfiable. If we cannot do that, then the function is not satisfiable or unsat. And SAT solver can basically exploit this observation to easily detect conflicts on assignment, meaning that it can say that okay, when this variable takes x 0, this variable takes 0, then the third variable cannot take 1 to make it satisfiable and so on. So, these kind of things, and what is conflict we will see in more detail. So, those kind of conflicting requirement, okay, that if this variable takes this and this variable takes this, the third cannot take this or so on, those kind of deductions can be done very easily by a SAT solver if a function is represented in a CNF representation. And based on it, the SAT solver can apply reasoning and reduce the search space. It can reduce the search space and find a solution, meaning that whether determine that whether a function is SAT or an unsat in an efficient manner. And another thing is that suppose there is a combinational circuit. Now, the combinational circuit is typically represented as a Boolean, as in terms of logic gates, or maybe as say Boolean logic network or some other representation. Now, if we are given a combinational logic circuit, we can easily transform that combinational logic circuit into a CNF representation in linear time and space. So, there exists an algorithm which can transform a given circuit to a CNF representation in linear time and space, meaning that it can transform it very efficiently. So, when we try to use when we try to use a SAT solver for solving VLSI related problem, what we do is that if we are given a combinational circuit, we can easily transform that combinational logic circuit into a CNF representation and then give that CNF representation to the SAT solver to produce the desired result. Now, we encounter various forms of SAT problems. We have different types of SAT problems are encountered in VLSI, and we call them as a SAT problem is called a K-SAT problem if each clause in the CNF representation of a Boolean function is of maximum k literals. Now, if we know that in a CNF representation, you will have many clauses, and each clause will have many literals. Now, how many literals are there allowed in how many maximum number of literals can appear in a clause, that defines what kind of K-SAT problem is. For example, let us see. Suppose the function is like this, given function is like this. Now, this function is in CNF representation. Now, this clause is of 2 literals, this is also of 2 literals, and this is also of 2 literals. Since the maximum number of literals in any clause is 2, we can say that this is a 2-SAT problem, meaning that 2 here represent the maximum number of literals appearing in the clauses. Now, let us take the next one, right. In the next one, we have 3 literals here and 2 literals and then 2 literals. So, the maximum number of literals in the clauses is 3, and therefore, it is a 3-SAT problem, right. And in next, let us see if in this function there are 3 literals, 2 literals and 4 literals. So, this is a 4-SAT problem. Now, the complexity of how complex a SAT problem is dependent on that how many literals are there in the clauses that we are given, right, and of course, also on the number of clauses that appear in the CNF representation. Now, if it is a 2-SAT problem, if it is 2-SAT problem, meaning that if we restrict all the clauses to have maximum of 2 literals, then the problem that we get is 2-SAT problem, and it turns out that 2-SAT problem can be solved in polynomial time, meaning that it is easier to solve in a polynomial time. But if we increase the maximum number of literal allowed in a clause to 3 and we consider 3-SAT problem, then 3-SAT problem is an NP complete problem. And what is an NP complete problem? NP complete problem is a difficult problem, and no known algorithm exists that can solve this problem in polynomial time for the worst case, right. So, NP complete problems are a specific class of problems which are known to be difficult, and for this class of problems the in the worst case the complexity will be will not be polynomial, right. So, in intuitive sense, an NP complete problems are difficult problems, and we need to use some heuristics to solve those problems. Now, k sat problem where k is greater than 3 is an n complete problem, meaning that if k is 2, then it is polynomial. If k is 3 or greater, then it is a NP complete problem. Okay. So, though SAT problem is an NP complete problem, meaning that if 3 SAT problem and above complex, if k is greater than 3, it is an NP complete problem. Nevertheless, there exist very efficient algorithms which can solve the SAT problem for many practical cases or many practical problems that we encounter in VLSI. Now, for a function of n variables, there are 2 to the power n possible variable assignments, right. So, in the worst case, we need to try all of them, right. So, if there are say n is equal to say 100 or 50, in this case the number of combinations that we need to try will be too many, 2 to the power say 100. It will be too many combinations to try one by one, and simply it is not feasible to solve a given SAT problem if the number of variables is large using a brute force, right. So, what do SAT solvers do? They do a kind of they perform a systematic search, and they prune the search space such that they need not explore solution in some regions of input combinations where solution cannot exist, right. So, they do not visit all possible cases, but they intelligently prune the search space such that a reduced space needs to be searched, and based on that it can either find a satisfiable problem or it can deduce that it is impossible to find a satisfiable problem and therefore satisfiable input combination, and therefore a given input Boolean function is an unsat Boolean function, right. So, typically what we use is what SAT solvers use is a DPLL algorithm, Davis, Putnam, Logman, Loveland algorithm or DPLL algorithm, and their variations are used mostly by SAT solvers. And what does this algorithm do? This algorithm basically heuristically assigns values 0 or 1 to unassigned variables, and based on that assignments it deduces the consequences of the assignments and determines forced assignment. So, it says selects a variable, it says that okay, let me assign it 0 or 1, and based after assigning 0 or 1 it deduces that okay, now if we assign this, what are the forced assignments, and what do we mean by forced assignment? Let us understand that. Now, there can happen that when we assign a value to a variable, there are other clauses where all the variables got assigned except one, right. If that happens, then we say that that clause has now become a unit clause. So, a clause in which all but one literal takes a value 0 and the corresponding forced assignments of the variable is known as implication, meaning that once we assign a variable 0 or 1 and maybe a group of variables we have assigned 0 or 1, then there can appear a clause in which all the literals are taking a value 0 except 1. Now, if that is the case, then we know that that particular variable which was not assigned will take either 0 or 1 based on its polarity, right. So, the forced assignment, the corresponding forced assignment is known as the implication. So, assignment of a variable leads to implications, and implication can further generate unit clauses and implications, right. So, let us take an example and understand it. Suppose we are given a function x1 plus x2 dot x1 dash plus x3 dot x2 dash plus x3. Now, this is a given Boolean function in CNF representation. Let us assign x1 is equal to 1. Now, if we assign x1 is equal to 1, then what happens to this clause? This clause gets satisfied, we need not worry about it. Now, what happens to this clause x1 dash plus x3? Now, x1 we have assigned as 1, so this becomes 0, right. Now, in this clause all but one variable, that is x3, is assigned a value 0. So, now what do we need to assign to x3? We are forced to assign 1, right, and therefore, x3 is equal to 1 is an implication, right. Now, if we assign x3 is equal to 1, now this got satisfied, or meaning that the first two clauses became 1. What about the third one, this one? Now, in this case we have assigned x1 x3, or we were forced to assign x3 is equal to 1. Therefore, this term, then this literal takes a value of 0, because it is x3 dash, right, because we have made x3 is equal to 1, x3 dash becomes 0. And in this particular clause we have only x2 dash unassigned, all others are 0, and therefore, we are forced to have x2 is equal to 0, such that this also becomes 1, right. So, the x2 is equal to 0 is an implication in this. So, when we made one of the variable, we assigned one of the variables, in this case x1 is equal to 1, there were forced assignments, or there were multiple unit, there was an unit clause, and therefore, we had an implication, and this implication led to another unit clause and another implication, right. So, given a variable assignment, there can be multiple forced assignments or multiple implications which can be which we are forced to make, and therefore, there is a task, or which is done by inside the SAT solver, and that task is known as Boolean constraint propagation. And in Boolean constraint propagation, what it does is that it deduces implications iteratively until possible. So, here we started with x1 is equal to 1, and then x3 is equal to 1, and x2 is equal to 0. These were forced, and these, so in Boolean constraint propagation, these implications will be deduced and propagated until it is possible, right, until it is possible. Now, sometimes the variable assignments can make a given clause, all of the literals of that as 0, right. So, if variable assignments and associated implications make all the literals in a clause evaluate to 0, then we have reached a kind of conflict. We reached a situation which is known as conflict, and then what we need to do is that we require to do a backtracking, meaning that some earlier decisions must be flipped. We need to toggle the earlier, if we have said chosen say n x1 is equal to 1, now we have to flip it and choose x1 is equal to 0. Then only we can proceed further, right. So, once we have chosen some variable assignment, and that led to implications, and we performed Boolean constraint propagation. As a result of that, we reached the point where for a given clause all the literals takes a value 0, then we have reached a conflict situation. And then what we need to do is that we need to go back, need to backtrack, and maybe toggle some of the variable assignment, so that the function it can become satisfiable. Now, for example, in this case, if we assign in this Boolean function, if we assign say x1 is equal to 1, right, we assign x1 is equal to 1, this gets satisfied, no issue. In this case, x1 dash is equal to becomes 0, So, we are forced to assign x3 is equal to 1, right. We are forced to assign x3 is equal to 1. Now, what happened? We in this case we for this clause, now this one if we have assigned x1 is equal to 1. So, this takes a value 0 and we have also assigned x3 is equal to 1. So, this also takes value. So, for this clause we have now got a conflict, right. We have got a conflict. So, all literals in this clause now become 0, and that means that we have now got a conflict and we need to backtrack. Backtracking means that now we have to toggle the value of x1 is equal to 1 and consider x1 is equal to 0. Now, suppose we make x1 is equal to 0, then we are forced to make x2 is equal to 1, right. And if we have made this x1 is equal to 0, so this becomes satisfied, and this we have also made this x1 is equal to 0. So, this one will also get satisfied and we have a satisfiable function. So, this is a satisfiable function, right. So, while doing assigning variable a conflict can be reached, then we have to backtrack. Now, when is a function satisfiable? If no conflict is encountered, the solver goes on assigning variables until all the variables gets assigned. Like in this case, we toggled it, we toggled the earlier assignment and we proceeded, then we reached a satisfiable solution. And if no conflict is and when we toggled it, we did not get any conflict. So, the solver goes on assigning variable until all variables get assigned and we reach the satisfiable or we say that the function is satisfiable. And when is function not satisfiable or when it is unsat? If we obtain a conflict and no more backtracking is possible, then we say that the function is unsatisfied. Okay. So, we go and try to toggle it, for example, from x1 is equal to 1 to x1 is equal to 0, but we found that earlier we had already tried x1 is equal to 0. So, now there is nothing to toggle, right. Now, if we have obtained a conflict and no more backtracking is possible, then we declare that the function is unsatisfied. Now, let's look into more into that how the code of this satisfiability solver may look like, right, a pseudo code for this. Now, for a sat solver, what do we give as an input? So, we give a function f as in the CNF form, and what is the output of from a sat solver? It returns sat if it is the function f is satisfiable, otherwise it retains a label which is unsat where if it is not satisfiable. And how will the code look like? So, we say that we start with a decision level of 0, we have not yet decided any variable. Then what we do is that we decide the value of a variable, right, for in the function f. Suppose f was having say 3 variables. So, first of all we decide the value of a Boolean variable, and if we are able to decide it and then we deduce that if that decision leads to conflict or not, right. So, suppose we assigned a value x1 is equal to 1. Now, if there 2 cases can happen, after assignment we did the Boolean constraint propagation and we got there was no conflict at all, right. If there is no conflict at all, we say that we just increase the decision level by 1. If there was a conflict, right, if we deduce and we find a conflict, then what we do, right. In that case, we backtrack one level, diagnose that which variable we want to backtrack, and then we if backtracking is not possible, we have exhausted all the possibility, then we say that it is an unsat problem, right, the function f is unsat. Otherwise, what we say is that backtrack to previous level or to some decision level, and then the algorithm moves forward. Now, if there is no conflict and we go on deciding variable and all get assigned, in that case we return that the function is a sat instance. right. Now, this is just a pseudo code for solving the SAT problem. The actual in actual implementation, the function decide, the function deduce, the function diagnose, and the function backtrack can vary from implementation to implementation. There is very much implementation specific, and different SAT solver choose various kind of heuristics to decide which variable to assign, or if given a conflict, which variable to backtrack, right. Some can choose that what the variable which was last assigned, that is backtracked, or some SAT solver can say that okay, I will backtrack that decision variable which led to most number of conflicts, and so on. So, all these things, decide, deduce, and backtrack, these things, these are very much implementation specific, and different SAT solvers can use various heuristics in this in implementing these functions. Now, the algorithm that we saw in the previous slide was just a bare bone organizations of various functions or tasks that is carried out during solving a SAT problem. Now, over the last 20 years, a lot of improvement has been made in the SAT solvers. For example, now SAT solvers intelligently do pre-processing of the given SAT problem rather than directly solving the given SAT problem. It first pre-process and simplifies the problem and then moves ahead, right. Or it employs very efficient data structures for Boolean constraint propagation, so that given an assignment, it can propagate the values of the or the effect of that assignment in a very fast and efficient manner. And it also prunes the search space very intelligently, so that it does not look into those areas or regions of the solutions where no solutions can be found. So, it intelligently prunes the search space and also selects some random restart strategy to quickly reach at the solution. And these days multi-core processing has made the SAT solver really fast. So, now the SAT solvers have become very powerful, and those are used in solving many VLSI design problem, as we will see in the subsequent lectures. Now, if you want to go deeper into the topics that I discussed today, you can look into these references. So, now let me summarize what we have done in last two lectures. In last two lectures, we have looked into formal verification, and we have seen that the formal verification techniques have become popular in VLSI design flow due to two core techniques. The first one was BDD, or the invention of BDD as a compact and canonical representation of Boolean function, and the second one was the efficient SAT solvers. Now, in the next two lectures, we will be looking at how these tools, this is BDD packages or Boolean representation using BDD, and the SAT solvers can simplify or help us solve VLSI design problems. Thank you very much.